Hey everyone, this video is going to be an overview of PS6 Python portion. It should help you get started on a lot of the theory questions. I'm not going to show the questions because I want this video to be transferable year to year. I'm instead going to talk about them and give you the problem number and the section it's under while I describe the different concepts you'll need. So the first thing I'm going to talk about is demodulation, handling lag. And the idea with this problem is we're trying to figure out why our cosine-based or heterodyne demodulator doesn't work for certain kinds of delay lags or phase shifts. So in order to understand that, I'm going to go back to talking about the unit circle. And so know you all hold near and dear in your hearts. That's not a straight line. There we go. Good. In the unit circle, if I'm just looking at the angle going around this circle, this is 0, this is pi over 2, this is pi, and this is 3 pi over 2. Now if I had gone around in this direction instead, then this would be negative pi. Doesn't really matter. Pi and negative pi are the same angle. And the idea with a phase lag is this phase lag is taking you from an original lag of 0, which is this vector right here, and it is rotating this vector around the unit circle based on the amount of phase lag. So say my lag was pi, my vector is going to rotate to pi. Say my phase lag was pi over 2 instead, it's going to rotate to pi over 2. Great. Now that we have that down, we're going to talk about why it sometimes messes up heterodyne demodulation when you have certain kinds of phase lag. So the idea behind heterodyne is that we're multiplying by a cosine, which means that if we have a phase lag of 0 or pi or some multiple of those, we're still in an area where cosine is fully expressed, because cosine at 0 is 1. And cosine at pi is negative 1. So we're able to get the entire magnitude, the entire amplitude of our original signal back. Now let's say our phase lag is maybe pi over 6, something like this. Well, now we're missing a little bit. Let me make this a different color so it's obvious. Now we're missing a little bit of our signal, right? We're missing this much, because some of that has gone over into sine territory. If our phase lag is instead pi over 3, up here, now we're missing even more of the cosine section, and we have much more represented in sine. That's not good, because that means we're losing a lot of that signal when we're demodulating with a cosine. And a worst case scenario is if we have a phase shift of pi over 2, cosine at pi over 2 is 0. If we try to demodulate with a cosine, we're going to get nothing back. It's all lost to sine territory. This is why when we do demodulation with a cosine and a sine, we do quadrature demodulation, we get a much better output because we're able to use both the cosine and the sine parts of our resulting signal in order to extract the original. With quadrature demodulation, if your phase lag is 0, everything is expressed in the cosine term right here. If your phase lag is pi over 2, everything is expressed in the sine term. And if your phase lag is anywhere in the middle, Well, you're able to use both the cosine and the sine sections, and that'll give you the amplitude of the original signal. So if you're running these tests and you think, wait, with a certain phase lag or with a certain delay lag, I'm not getting my original signal back, my heterodyne demodulation isn't working, check to see how much in cosine or sine territory you're in. Or in other words, is your phase lag close to a multiple of pi, or is your phase lag close to a multiple of pi over 2? Great. The next topic I want to talk about is with handling multiple senders. Now the idea behind this is that we know if we modulate and demodulate with the same frequency, cosine omega c, cosine omega c, right, modulate and demodulate, then we get a signal that looks like this. Centered at 0 with 2 omega c and negative 2 omega c. But that's only because we use the same carrier frequency both times. If I had instead decided I was going to modulate with cosine omega c and demodulate with cosine omega d, I'm not going to get 3 peaks. I'm going to get 4 peaks. I'm going to get a peak, 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 peak. Now it's up to you to figure out where those peaks end up, but take a look at why this formula only gets you 3 peaks, and you'll realize it does really get you 4. 2 of them just add up to get you that larger peak in the middle. The other thing I'd like to talk about here is averaging filters and how they work. The idea with an averaging filter is that to find the filtered value of this point here, it's going to take the average of its neighboring points and then change this value to the average of, let's say, y1 to y2. Which means that if I have some noise way out in my signal, I have like a little noise here and a little noise here and a little noise here. Because of this averaging filter, the average of this whole section is a lot closer to 0 than just the value right here. So that's going to actually decrease this noise and bring it down. If I instead have an averaging filter, and I maybe have, some real values going on here, and I want to find the filter's version of the point here. If I take the average of this window, the value of this point is not going to be equal to 0. It's actually going to be greater than 0 because all of this and all of this add up to give me a non-zero average. So there's some caveats to the averaging filter and some pitfalls you might fall into. So definitely be careful of that. And I believe that is all I wanted to talk about. Oh, one more thing actually. And this is just a more conceptual topic. When we talk about 8 of omega, and this is still part of multiple senders. When we talk about 8 of omega produces some sort of gain. And that gain is the magnitude of h of omega. The magnitude of h of omega, when represented as a complex number a plus bj, is a squared plus b squared square rooted. Or you can just plug some omega into h of omega and separate the phase section, which is going to be your e to the something, and your magnitude, which is going to be the coefficient multiplying a complex exponential. So you have h of omega equals a e to the negative j omega k, then this is your magnitude of h of omega. And that magnitude tells you how your signal is going to be amplified given the frequency your signal is at. So if I plug an omega, let's say equal to like pi over 3 into h of omega, and I get a magnitude of h of pi over 3 to be like 0.001, nothing I send into this channel at a frequency of pi over 3 is really going to come out because it's going to be attenuated to such a small signal. Whereas if I have omega equals, say, 5 pi over 6, and I plug that into h of omega, and I get my magnitude at 5 over 6 pi equals 7, that means that any signal I send in at frequency 5 pi over 6 is going to be amplified 7 times. This is really good. And you can kind of think about what this means when it comes to filters. It means that if you have some frequencies that you don't want to go through, then you can choose an h of omega where the response at those frequencies is really small. And if you want to say let some low frequencies through, like a low pass filter, then you can choose an h of omega where the magnitude at low values of omega is really large. Anyways, that's it for the Python section. If you have any questions, go into office hours or ask on Piazza, and I hope this was helpful.